Hi class, this section is on complex and rational zeros of polynomials. So the first theorem says that conjugate pair zeros of a polynomial. So if you have a polynomial f of x that has degree n greater than 1 and it has real coefficients, then the conjugate will also be a zero. So if you have a zero that's in the form of a complex number, the complex conjugate also has to be a zero. So they must come in pairs. So for example, if this polynomial here has degree 4, and it tells you that there's two zeros that are 4 plus 3i and negative 2 plus I, that means the other two zeros would be the complex conjugates. So for example, we have this one is a 0, which means that 4 minus 3i must be a 0. And then if negative 2 plus I is a 0, then that means that negative 2 minus I must also be a 0. So in order to find the polynomial of degree 4 with real coefficients, we must expand these out by creating their factors. So the factor for the first one would be x minus parentheses 4 plus 3i. The second factor would be x minus parentheses 4 minus 3i. And then the next one would be x minus parentheses negative 2 plus I. And then the last one would be x minus negative 2 minus I. Notice they all have the same general form of x minus c, where c is a 0. So x minus c, x minus c, x minus c, and x minus c. Now we would distribute the negative into each of these, and we get, so we're going to get x minus 4 minus 3i for the first one, x minus 4 plus 3i, x plus 2 minus I, and x plus 2 plus I. So we're going to multiply these four factors out, but we're going to multiply two at a time, and we're going to multiply the conjugates. So this one times this one. Let's do that on the next page because we're going to run out of space. So if we do that, we're going to get, the first factor was x minus 4 minus 3i. I'm going to do a 3 by 3 box. I think it's the easiest way. So the first one was x minus 4 minus 3i. And the other one would be x minus 4 plus 3i. Yes. And now we can multiply the row and the column to get each box filled out. So this would be x squared minus 4x minus 3xi, negative 4x plus 16 plus 12i, 3xi, negative 12i, and negative 9i squared. But we know I squared is negative 1. So this is really going to be positive 9 because you have a negative 9 times a negative 1. Now we can combine like terms. As you can see, these will cancel each other out. These will cancel each other out. These we can combine, and these we can combine. So the final product will be x squared minus 8x. Since this is really a positive 9, we have 9 plus 16, which is 25. Then we're going to do the same thing to the other two factors. So we create a 3 by 3 box once again. And we do a similar thing with x plus 2 minus I, x plus 2 minus I, and x plus 2 plus I believe the next one is x plus 2 plus I. Great. And now we would do the same thing. X squared, 2x minus xi, 2x, 4 minus 2i, xi, 2i, negative I squared, which is really negative 1, which is really positive 1. Because you have a negative times a negative, which is really going to be a positive 1. So these cancel each other out. These cancel each other out. We have like terms and like terms. So this is going to be x squared plus 4x plus 5. The 5 is because you have a 4 plus 1. Okay, and now we can multiply these two out, Actually, I don't think we even need to go that far. All right, so that's all you really need to do. Just write these two factors out as a product. So it would be x squared minus 8x plus 25 times x squared plus 4x plus 5. So the goal is to not have any imaginary coefficients or any imaginary units involved. So all these i's must not be there. And that's why we multiplied the conjugates together. And that's how we got rid of the i's. And this is the final answer. The next theorem says if a polynomial has integer coefficients and if c over d is a rational zero of f of x such that c and d have no common prime factors, and the numerator c of the zero is a factor of the constant term a sub 0, and the denominator d of the zero is a factor of the leading coefficient a sub n. So that's a little wordy. Once again, I'm going to just kind of walk you through this problem, and you'll see how that theorem applies. So this, you can think of this as your c, or factors. Yeah, just call that c. Call this d. And so we're looking for c over d is what the theorem says over here. So, but this is really, we need to break up 5 into all of its factors. So the factors of 5 would be plus or minus 1 is a factor of 5, and plus or minus 5 is a factor of 5. There's only two factors, 1 and 5. There's really 4 because of plus minus. And then same thing for d. Well, the factors of 3 are 1 and 3, so therefore 1 plus or minus 1 or plus or minus 3. So what this is saying is if the only possible rational zeros of this function would be of these values. So the possible rational zeros are going to be, well, any kind of combination of these two numbers divided by these two numbers. So you can start off by plus or minus 1 over 1 or plus or minus 1 over 3. So that would be or you have plus or minus 5 over 1, or you have plus or minus 5 over 3. So it's any combination of this over this, or this over this, or that over that. So there's 2, 4, 6, 8 possible zeros that are rational. So we'd have to go, and they're saying show that the polynomial has no rational zeros. So the way we would do that, this is going to take a while, is you're going to use your synthetic division. So we'll start with positive 1, put that in the upper left corner, and then write out the coefficients. So the coefficients are 3, negative 4, 7, and 5. We bring down the first term, multiply, add, multiply, add, multiply, add. So as you can see, since the remainder is not 0, 1 is not a 0. So what they're saying is that this polynomial has no rational zeros. So in order to prove that, you would have to go through each of these and confirm that for each one, the remainder is not 0. Let's do one more. I'll do 1/3. So once again, you write out the coefficients, and you bring down the first term. If you multiply, you get 1. If you add, you get negative 3. If you multiply, you get negative 1. If you add, you get 6. If you multiply, you get 2. And as you can see, the remainder is not 0. So I showed that two values, positive 1 and positive 1/3, are not zeros of this polynomial. So what you would have to do is you would just have to do it for the rest of them. For negative 1, negative 1/3, positive 5, negative 5, positive 5/3, and negative 5/3. And that's how you would show that this polynomial has no rational zeros. The next example says find all rational zeros of the equation. So we're going to use that theorem. So you want to call this one C, this one D. So D is 1 because of the leading coefficient. So we're looking for all the possible values of c over d, where c represents all the factors of negative 24. Well, the factors of 24 would be 1, 2, 3, 4, 6, 8, 12, and itself, 24. Those are all the factors of 24. And the factors of 1 is itself 1. So the possible rational zeros of this polynomial are just going to be the numerator. And as you can see, there's 1, 2, 3, 4, 5, 6, 7, 8 times 2 is 16 possible rational zeros. So we hope to get lucky by using synthetic division and getting a remainder of 0. So let's try 1 and hope that that one gives us a remainder of 0. So the coefficients are 1, 1, negative 14, negative 24. You always want to make sure that there's no missing terms. 3, 2, 1, 0, which there are not. So if you bring down 1 and you multiply, you get 1, then you add, then you multiply, then you add, and then you multiply. And this is not equal to 0. So that one is not a rational 0. So then we move on to the next one. I'm going to try negative 1. Bring down the first term, multiply, add, multiply, add, multiply, add, and you get negative 10, which is not 0. So we move on to the next number. And like I said, we hope to get a 0 remainder soon. So it is a little tedious. Bring down the 1, multiply, add, multiply, add, multiply, add, and we get negative 40, I believe. So let's try negative 2. Multiply, add, multiply, add, and what do you know? We finally get 0 remainder. So we found 1 0, negative 2 is a 0. And then the good thing about this is that instead of repeating this process over and over for the rest of the numbers, once you're left with the trinomial, you can factor that trinomial. So this trinomial here will be x squared minus x minus 12 equal to 0. If you factor that trinomial, you will get x minus 4, x plus 3, and therefore the two other zeros are given by these two factors, which are 4 and negative 3. And at most, this polynomial has to have at most 3 zeros because of the degree. The degree is 3, therefore, at most, it has to have 3 zeros, which it does. 1, 2, 3. So whenever you have a third degree polynomial, your goal is to find one instance where the remainder is 0. Once you get that 0, then you can just factor the trinomial that's left and to get the other zeros. If it's not factorable, you can also do the quadratic formula, and that would give you the other 2 zeros. All right, same directions for this problem. This one might be a little bit harder because it's a 5th degree instead of a 3rd degree, but it works the same way. First thing you should actually do is take out the GCF. The GCF here is x squared. So you're left with 6x to the 3rd plus 19x squared plus x minus 6. We already know the zeros for that are x equals 0, multiplicity 2, because of the exponent. All right, and so basically all we need to do is just treat this as a separate polynomial that's degree 3, just like we had this one here. So let's do that. Let's find the c over the d's. C over d. C over d is going to be all the factors of 6, which are 1, 2, 3, and 6. And same thing for the denominator. Since it's 6 as well, it's going to be the same exact thing. All right, so let's start with the first one. When we divide by 1, that just gives us the remainder. So the possible rational zeros are going to be plus or minus 1, 2, 3, 6. All right, now let's move over to 2. So divide all of these by 2, you'll get plus or minus 1/2, plus or minus 1, which is already there, plus or minus 3/2, and then plus or minus 6/2 is 3, which we already have. All right, now we move to the next one, 3. So 1/3, 2/3, and then 3/3, which we already have as 1, and then 6/3 we already have as 2. So then we move on to the next one, which would be 6, so that would be 1/6. 2/6 is 1/3, which we already have. 3/6 is 1/2, which we already have, and 6/6 is 1, which we already have. So these would be the total possible rational zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9 times 2 is 18. So there's a total of 18 possible rational zeros. So let's hope to get a 0 remainder. I'm going to start with 1. The coefficients are 6, 19, 1, -6. Let's bring down the first term. Let's make sure there's no missing terms. 3, 2, 1, 0. All right, multiply, we get 6. Add, we get 25, multiply 25, add 26, multiply 26, and as you can see, this is not remainder 0. So let's try -1. Okay, so 6, 19, 1, -6. Bring that down, multiply, add. You're going to get, what is that, 13. Multiply, -13, add, -12. 12, and that is 6. Okay, so let's try 2. So 2 would be 12. That's going to be 31. Multiply is 62, 63. Multiply, that's definitely not going to be 0. Let's try -2. It's going to be 6, that's going to be -12, 7, -14, that's -13, that's going to be 26, that is going to be 20. So we're not having any luck. Let's try 3. I'm going to have to open up a new page. 3, and the coefficients are 6, 19, -1 and 6, I believe. Let me double check. +1 and -6. Let's hope we get lucky here. Multiply, you get 18. Add, you get, what is that? That's going to be 37. Multiply, you're going to get 111, and that's definitely not going to be 0. So let's try -3 now. -18, add, you get 1. That's -3, that's -2. Wow, we finally get 0 remainder. And like we said, this is our trinomial that's left over, 6x squared plus x minus 2. And if we can factor this, that would give us the other 2 zeros. I'm going to try 3x times 2x, and I'm going to try 2 and 1. To get the middle coefficient to be 1, you would have to do 4, take away 3. So 4 positive minus 3. And this is going to give us this. If you were to multiply these two factors out, you can confirm that. And now the 2 extra zeros are going to be, when we solve these two factors, x equals -2/3 and x equals +1/2. So those are the other two zeros. So the three zeros are -3, -2/3, and 1/2. Notice that the three zeros are part of the possible rational zeros. They're in this list of values. All right, so that's what they wanted us to do, to find all rational solutions, of which we know there are 5, 2 here, and 3